Section 5.2 Exponential Functions. In this section we're going to talk about exponential functions. So let's start by defining an exponential function. Okay, the exponential function, I'll abbreviate that exp, with base b is defined as f of x is equal to, it's a function, so we have f of x is equal to b to the x, where the exponent is my independent variable. Remember, x is the independent variable, f is a dependent variable, or y is a dependent variable. Okay, where b is greater than 0, okay, and okay, b is not equal to 1, okay, and x is any real number. Also, x is any real number. So that's a definition of an exponential function. Okay, so let me give you some examples. I could have f of x is equal to 2 to the x, or I could also have f of x is equal to 2 to the x minus, I'm sorry, let's use a different base. I say I have 3 to the x minus 2, or I could also have an example like this: f of x is equal to 1/2 to the x, and so on. So these are just examples of exponential function. You could also have something like this: f of x is equal to minus 4 to the negative x. Okay, so these are all examples of exponential functions. Alright, so now that we know what an exponential function is, it's a function that looks like this, where b is my base and my exponent is the independent variable. Okay, right, so let's start by obviously taking a look at the graph of an exponential function. Okay, so we'll start by taking a look at the graph of an exponential function. So I'll take a look at two examples. Let's say if you have f of x is equal to 2 to the x. Now, to graph this, anytime you're graphing something for the very first time and you don't have any tricks to graph it, you just use brute force. So let's use brute force and graph it. So you just pick some x values, find the corresponding y values, and then you create a point, which would be x and y. So I'll pick -2, -1, 0, 1, and 2. Okay, so we get y is equal to 2 to the -2, so you get 1 to the 2 squared, using the property of exponents to make it positive. So you get 1 over 4. So we get x is -2, y is 1/4. Then we get y is equal to 2 to the -1, which is 1 over 2. So when x is -1, y is 1/2. Then we get y is equal to 2 to the 0. Anything raised to 0 is 1. So when x is 0, y is 1. Y is equal to 2 to the 1. So you just get 2. When x is 1, y is 2. Y is equal to 2 to the 2 is equal to 4. So when x is 2, y is 4. Now I'm just going to show you what's happening just to prove to you. Let's say when x is 6 for that matter, well, you get y is equal to 2 to the 6, which is 64. So you can see when x is 6, y is already 64. And if you take when x is 8, you'll get 256, and so on. So you can see as x is getting bigger, y is getting bigger much faster. Okay, so keep that in mind. We're going to use that, we're going to state that in a second. So let's graph this. Okay, so we have 1, 2, 3, 4. We have 1, 2, minus 1, minus 2. So my points are when x is negative 2, y is 1/4. So if this is 1/2, 1/4 would be further down. When x is minus 1, it is 1/2. When x is 0, it is 1. When x is 1, we have 2. And when x is 2, we have 4. So if you were to connect these points, it looks like this. Okay. Now, a couple things to write down about this while we have it here. What is the domain of this function? The domain is all the x values for which you have a corresponding y value, of all the inputs for which you have an output. And you can see it doesn't matter which x value I pick on the left or the right, there's always going to be a point on the graph. I just stopped drawing the graph here, but this graph technically keeps going this way and this keeps going this way. So the domain is just going to be every real number, because there's no x value that's going to not produce a y value. Every x value is going to produce a y value, because if you take this x value, there's a point on the graph. If you take this x value, there's a point on the graph. If you take this x value, there's a point on the graph. So as soon as there's a point on the graph, there's going to be a corresponding y value. Okay, so the domain is that, and the range is what here? Range is all the y values for which you have a point on the graph. For example, if y is minus 1, if you go horizontally across, do I have a point on the graph? If I don't have a point on the graph, then there's no corresponding x value. Like for example, for this y value, if you go across and down, you have a point on the graph. So that y value is in the domain, is in the range, because there was an x value that generated that y value. So you can see that the y values start generating from 0 all the way up to positive infinite, but not including 0, because there's no value of x. For example, if y is equal to 2 to the x and you want to find if y is 0, there's no value of x that's going to make this expression 0. 2 raised to no number is going to be 0. So that tells me, okay, that y cannot be 0. So my range is going to be 0 to infinite, not including 0. Okay, so that's something neat to know. The other thing to note is, as x gets bigger, goes in this direction, as you're going in this direction, x is getting bigger, what's happening to the y value? They're getting also bigger, aren't they? I just told you that when x is 6, y is already up to 64. When x is 8, it's up to 256. And when x is 9, it's 512. When x is 10, it's 1024, and so on. So you're getting big very fast. And that's why in magazines and newspapers and things like that, and research articles, anytime they want to emphasize that things are growing really fast, they always say it's an exponential growth, because exponential growth implies that things are growing very, very rapidly. So as x goes to infinite, this implies y also goes to infinite. It's getting bigger and bigger, so the function is going to infinite. On the other hand, as x goes to negative infinite, when x is getting smaller, okay, what's happening to the y values? They're going to 0, because they're getting smaller and smaller, but they're never going to be 0, because like I told you, y is never 0. Okay, so we know that. So y is never going to 0. So y approaches 0 but never is 0. So these are some of the things you should know about the exponential graph, and I'll write them down again. Okay, let's go ahead and take a look at another exponential graph. Let's say if I have f of x is equal to 1/2 to the x. Okay, here's my x, my y, and my point x and y. So let's just pick the same values again and see what happens. Okay, so let's say I have y is equal to 1/2 to the negative 2. Because it's a negative exponent, to make it positive, I'd have to flip that whole fraction, or I can distribute it. I can do it this way: 1 raised to negative 2 and 2 raised to negative 2. Then I can make that positive by sending this up and bringing this down. So I get 2 raised squared over 1 squared, so we just get 4. So you can see we just get 4, so we get negative 2 and 4. Same thing, I have 1/2 raised to minus 1. That's the same thing as 2. Just use the same logic here, except instead of minus 2 we have minus 1. So we get minus 1 and 2. When y is 0, any number raised to 0 is always 1, so we get 0 and 1. When y is 1, we get 1/2 to the 1, which is just 1/2. And when y is 2, we get 1/2 to the 2, which is 1 squared is 1, 2 squared is 4. So we get this. So these numbers look a lot similar to the last graph, and they are, because now what happens? We have 1, 2, minus 1, minus 2. So when y is negative 2, when x is negative 2, y is 4. So we have this point. When y is minus 1, x is 2. When y is 0, it is 1. When y is 1, it is half. And when y is 2, it's quarter. So you can see now the graph's going this way. So it's pretty much the same graph as the last one, except now in this graph we say it's increasing, or we say it's a growth. Okay, we say it's a growth because things are getting bigger. In this graph we say it's decreasing, because as we go from left to right the graph is going down, or it's a decay, things are getting smaller. So it's the same idea, except now things are getting smaller. Okay, so those two are pretty much the same thing. The main thing to take away from both those graphs is they do have a lot of things in common. The domain is still the same. The domain is minus infinite to infinite, and the range is still the same from 0 to infinite. Now this time when x gets big, what's happening to the graph is x is getting bigger, y is getting smaller, so it's going to 0. On the other hand, as x gets smaller, this time what's happening is x is getting smaller, y is getting bigger, so y is going to infinite. Okay, so those things are the same as what we had. Pretty much it's just swapped around now because the graph is flipped about the y-axis. The only other thing that they both share in common is this. When x is 0, y is 1. That is something they both share in common. And that's a property of exponential graphs. Okay, so or exponential functions for that matter, because whenever the exponent is 0, doesn't matter what the base is, the value is always going to be 1. Okay, so let's write some of this stuff down and call it the properties of exponential graphs. So if you want to graph exponential functions, you can do this. Actually, before I give you the properties, let me show you. We can also use our little bag of tricks on. So all exponential functions all graphs of exponential functions look like this. Basically, they always go through the point. Their y-intercept is always 1, so 1 0 0 1. But so if I asked you to graph this x 3 raised to x minus 2, okay, so I can graph this. It's going to be pretty much the same as what I had before. Okay, when I had 2 raised to x, except now I have 3 raised to x. The key thing is anytime this number is bigger than 1, then the graph is going to look just like a growth graph always. Okay, so the only thing that's going to change is because instead of x we have, let me just make this a 2, it'll be easier. Instead of x we have x minus 2. So when we change x to x minus 2, what do? We do a horizontal shift, right? Remember shifting? So we'll shift in which direction? Because it's a horizontal shift, it's in the opposite direction of the sign, so we'll shift 2 units to the left. 2 units to the right. So normally this point here, this was what, 0 1, this point will shift and come here. Remember that every point shifts. Let me just draw the regular 2 to the x. This is what 2 to the x looks like. We drew that earlier today. It always goes through 1. The y-intercept is always 1, so it always goes through 0 1. But now because of x minus 2, this graph gets shifted 2 units to the right. So now it'll go through this point. So the graph we are looking for is going to look like this. It's going to still have the same shape, but it's going to go through this point. So that's a graph of this. So we can use the same graphing techniques that we had before. So if I asked you to graph something like this, let's say I have minus 2x plus 1. If I get rid of this negative and the 1, you know what this graph looks like. We just did that, right? It's something like this. So what does the minus do? Let's start with the minus first. What does the minus do? Anytime you have a negative in the front, it flips the graph, right? So this graph would look something like this. So instead of this shape, it will be this shape. It still goes through minus 1 because before it went through plus 1. Okay, the y-intercept was plus 1, now it will become minus 1. You just flip that graph about the x-axis because that's what that does. Negative does gives you the reflection. What does a 1 do? So you take this graph and add 1 to it. So if I take this point and add 1 to it, this negative 1 will become 0. Okay, and then I have an basically this is really an asymptote because the graph's getting closer and closer to that line, right? So this asymptote, which is at 0, y is equal to 0, will move up 1 unit because you're adding 1 to that too. So my final graph would look something like this. I would have an asymptote now at 1, and this point will become 0, so my graph would go like this. So here's a graph of this function, y is equal to negative 2x plus 1. So you can see it's not that difficult to draw these graphs. Once you know those graphing techniques, you can draw rough sketches very quickly by using those graphing techniques. Okay, and we'll come back to doing a couple more examples. Let me go ahead and give you some properties of exponential functions. And then we'll talk about this particular function. F is equal to function f of x is equal to b to the x. So this is the one we are talking about. Okay, so let's talk about that. 1, okay, the domain is always minus infinite to infinite, so it works for all numbers, and the range is from 0 to infinite. We talked about that. The y-intercept is always 1 and 0. I showed you that. And there's no x-intercept. And you can see that from both these graphs. Okay, in this one they were shifted around, so that's why there was an x-intercept. With this one, you notice it never crosses the x-axis, and this one never crosses the x-axis, so there's no x-intercept. It crosses the y-axis at 1, 0, but it gets closer and closer to the x-axis here. Similarly, it gets closer and closer to the x-axis in this direction, but never crosses it. Okay, so there's no x-intercept 3 for this particular one. But if I start changing it, like this one, I changed it. Do you follow? I tried to graph this. There was an x-intercept at 0 there. Okay, but we're talking about this basic generic exponential function. Okay, the other thing is f is continuous. There's no gaps in it. You can see that the graph is continuous and smooth. There's no sharp edges, sharp spikes in it or anything like that. Okay, so that's another nice thing to note about the exponential graph. The other thing to note is if b is greater than 1, then the graph increases from left to right. So if b is greater than 1, so it looks something like this, so it goes up. It's exponential growth, we called it earlier. We call it a growth. On the other hand, if b is less than 1 and greater than 0, then the graph decreases from left to right, and we drew that also. It went like this. When b was a half, you notice that it was a decay, so we called it a decay. Okay, it was decaying. When b was 2, it was going up. When b was 1/2, it was going down, because b was between 0 and 1. The next thing, the most important thing to note here is, note, if you look at either one of these graphs, this one or this one, let's take a look at that. You can clearly see if I draw a horizontal line here, it only crosses the graph once. So what does that tell me? Or you can also notice the function is always going up, so it's always increasing here. So from those two things, what can you conclude? That the function is 1 to 1 and has an inverse. Okay, so f of x is a 1 to 1 function, is an 1 to 1 function, and hence has an inverse. So this is an important thing that we need to keep in the back of our head for the next section. This function is 1 to 1, so it'll have a inverse. So that is the most important thing I want you to take away from here. Okay. Alright, so now that we know all of this, let's quickly talk about one special exponential function. Okay, there's one function that's a special exponential function. Okay, and we call that the natural exponential function. Okay, and it's denoted by f of x is equal to, where the base is e to the x. So what is e? Where e is the irrational number. Irrational means a number that cannot be written as a fraction. It's the opposite of a rational number. Rational numbers can be written as a fraction. Irrational is a number that cannot be written as a fraction. Another way to look at it is it's a decimal number that never terminates. It just keeps going on and never repeats. A classic example of an irrational number is pi. And this is another example where e is an irrational number. E is equal to 2.71828169 and so on. All calculators have a key for e on them. Okay, so if you look at this calculator, your Texas Instrument, there's a key for e right there. You have to press the second key first and the division key, so you can go second divide. Oops, turn it on. You can go second division, you get e, and if you raise that to 1, you get the value of e. Okay, so 818282 again, not 69, sorry about that, and so on. So it's an irrational number. Okay, it's also referred to as Euler's number, named after the mathematician Leonhard Euler. So you can think of it as Euler's number. So this is a special exponential function. Okay. Alright, so now that we talked about exponential function, let me just give you some more examples of graphs of exponential functions that are just moved around so you guys can get comfortable with them. So let's say if they ask you to graph this, f of x is let's pick 4/5 raised to x. Now 4/5 is a number that's between 0 and 1. The base is between 0 and 1. So you know my graph is going to look like this. I don't even need to pick points. You know it's going to be a decay. It's going to go through 1. There's my graph of that. Okay. On the other hand, I'm sorry, not examples. On the other hand, if they asked us to graph this, we have 2/3 raised to negative x. Okay. Alright. So we have 2/3 raised to minus x. Alright. So let's take a look at it. Well, let's ignore the minus for a second. If I have 2/3 raised to x, that looks just like this because it's a decay, because this number is between 0 and 1. If you recall from this chapter 3, when you change x, when you put a negative in front of x, that flips the graph about the y-axis this time. That flips it about the y-axis. So let me just draw a couple different graphs here just to show you. So the first thing is this graph, without the negative, this graph looks like this. It's a decay. So this is the graph of y is equal to 2/3 raised to x. But because we have a negative x here, so that will flip it about the y-axis. So if you flip it about the y-axis, this piece will go to this side, this piece will go on this side. So the graph, oops, different color. So the graph would look like this. So this is the graph of y is equal to 2/3 raised to minus x. So you can see we're using the graphing techniques to graph these. So sometimes, you don't have to use brute force and draw a table and do it. If you now that we know some properties about exponential graphs, we can draw them very quickly. Okay. Here's another example. Let's say if I have 3 times 2 raised to x. If you remember, what happened when you multiplied a base graph by 3 in the front? If the number was between 0 and 1, then it was a vertical shrink. If the number was greater than 1, then it was a stretch. So in this case, if you think about it, let me draw 2 graphs again. Let's assume we don't have a 3 there. Then the graph looks like this. So this is the graph of y is equal to 2 to the x. Okay. Now what's going to happen? Because I'm multiplying by 3, everything is going to be stretched vertically. Everything is going to become taller. Okay, so this point, which is always 1, when x is 0. So when x is 0, you get 2 raised to 0 is 1, and now you multiply it by 3. So this point will jump up to 3. Okay, so this graph will look something like this. It'll still be a decay, except it'll be going up quickly. So this will be 3. So this is the graph of y is equal to 3 times 2 to the x. So in this case, everything is going up quickly. If I had multiplied by 1/3 instead, what does that do? It shrinks everything vertically. Okay, so then if this is the graph of y is equal to 2 to the x, now what will be the graph of 1/3 2 to the x? This point, which is 1, if you multiply this by 1/3, it'll come down right there. So the graph would look something like this. So there's the graph of y is equal to 1/3 2 to the x, because everything shrunk vertically. You notice these points came down, so everything is shrinking vertically. When you multiply by something between 0 and 1, out here everything is stretching vertically, everything is getting taller. Okay, so you can see there's some examples of exponential graphs. So what do you think the graph of e would look like? E is just an exponent. E is a number which is 2.71828182 and so on, right? So it's bigger than 1. So we know that this graph is going to represent a graph something like this, which is going through 1, because e to the 0 would be 1. So there's a graph of e. Okay, but the main thing, like I said, to take away from this section is that exponential graphs represent growth and decay depending upon what the base is. And the other thing to take away is exponential functions are one-to-one, or they're either always increasing or they're always decreasing. So they have an inverse. That's the most important thing, because that's the focus of this chapter. What is the inverse of the exponential function? Okay, and that's why we talked about inverse functions in the last section. And just quickly, if you're not familiar with the power functions keys, if you want to graph these on your calculators, you can just go y equal to, and then you can go e, so you can go second and divide raised to x, and then you can go to window and you can give it a value and you can graph it. There's your exponential function. Okay, so you can graph these on your calculators too. And that's pretty much it about this section. There's nothing that difficult in this section. There are some graphs that you have to draw and things like that using shifting and things like that, that's something you can do. Okay.